In this video, we're going to talk about coordinate mappings. So I want to begin with a theorem. So if we let B contain the vectors b1 up until bn, so if this is a basis for some vector space V, what I call the coordinate mapping is a function, so the way I'm going to notate it is I'll write t subscript b for my basis. So this is a function where the inputs are vectors in V, in my vector space, and the outputs are going to be things in Rn. So the coordinate mapping is going to take things in my vector space and output vectors in Rn. So the function, what it does is it inputs a vector x that's in my vector space, and it outputs the coordinate vector. And like we saw last time, the coordinate vector is going to be something that's in Rn. So it turns out that this is a linear transformation, and more importantly, this linear transformation is invertible. And so I want to introduce a little bit of terminology. When we have an invertible linear transformation, this is often called an isomorphism. So an isomorphism. So the idea behind this theorem is that when we're working with vector spaces that are more complicated than Rn, for example, like polynomials, if I need to answer a question about polynomials, like for example, if they're linearly independent or not, I can translate those polynomials to their coordinate vectors and then answer that question in terms of the coordinate vectors, because that'll be easier. So let's look at an example. So let's say we're working with polynomials, and I want to practice converting polynomials to coordinate vectors. So we know that B, which is the basis that contains 1t squared up until t to the n, this is what's called the standard basis for Pn. Pn is the set of polynomials of degree at most n. Okay, so let's consider some arbitrary polynomial in Pn. So I'll call it P of t. So this will have some constant term a0 plus a1t plus a2t squared plus plus an t to the n. So something in Pn looks like this. Now, let's convert this to its coordinate vector. So when I write the coordinate vector for P of t, so this is my notation for the coordinate vector. Remember, what this means is, tell me what the weights of the linear combination are. So when we've written P of t in this way, notice that we've written it as a linear combination of the elements in the basis. So the weights of this linear combination become the entries of our vector. So the first weight is a0, because it's technically a0 multiplied by 1 here. And the next weight is a1, the next weight is a2, all the way up until an. So notice I'm taking these coefficients, the a0, the a1, the a2, all the way up until an, and those are the entries of this vector. Okay, so what we now have is we have a vector in R n plus 1, because there are n plus 1 entries in this vector. And this is really powerful, because what this is going to let us do is express elements of arbitrary vector spaces as just simple vectors in Rn. So let me add that, as vectors in Rn, which we are more comfortable with. So let's look at a specific example where we use this. So here's the example. So is the following set of polynomials linearly independent, so that's what Li means, in P2. So P2 means we're talking about polynomials of degree at most 2. So before we get into it too far, notice that x plus 1 quantity squared, that's the same thing if I were to expand it as x squared plus 2x plus 1. And expanding that, that's going to make my computation more simple. So let's write each of these polynomials as a coordinate vector. So to do that, I need a basis. I need a basis in P2 that I'm going to work with. So let's just work with the standard basis. Oops, sorry, I didn't mean to write is there. So let's say that my basis, so if my basis contains 1x and x squared, so that's my basis. This is the standard basis. This is the standard basis for Pn, in this case P2. Now what I'll do is I'll take each of these polynomials, so for example x squared plus 2x plus 1, and translate that and write this as a coordinate vector. Okay, so the first entry that I write is the coefficient of 1, which is technically this one right here. The next entry that I write is the coefficient of the x term, which is 2. And the next entry I write is the coefficient of the x squared term, which is 1. Okay, so that's translating this polynomial in terms of its coordinate vector. Let's do the same thing for the next polynomial, which is x squared. If I rewrite that in terms of its coordinate vector, well, there's no constant term, there's no x term, but there is an x squared term, and its coefficient is technically a 1, so I'd write 1 there. We have one more polynomial, which is x plus 1. So its coordinate vector, well, the constant term coefficient is 1. The coefficient of x is 1, but there's no x squared term, so that coefficient is 0. Okay, so we have these three coordinate vectors. So what I'll do now is I'll test to see if these three coordinate vectors are linearly independent. And we know how to do that. We put them in a matrix. So first I'll write 1, 2, 1 as a column, and then 0, 0, 1 as a column, and then 1, 1, 0 as a column. And we would check to see if there's a pivot in every single column. That's how we check to see if vectors in Rn are linearly independent. Okay, so to do this, we would have to row reduce. Just to save time, I'm going to tell you guys what this row reduces to. So after a couple of row operations, this becomes 1, 0, 1, 0, 1, negative 1, and then 0, 0, negative 1. That's what it row reduces to after a few row operations. So if I call this first vector v1, this next coordinate vector v2, and this third coordinate vector v3, what we now know, because there are pivots in every single column here, we know that v1, v2, and v3, this set of three vectors, this is linearly independent. It's linearly independent in R3 because there was a pivot in each column. And as a result, the polynomials that they corresponded to, let me just call them P1, P2, and P3 for short, those polynomials are also linearly independent, but they exist in P2. So that's why this theorem is so important, because it lets me handle elements of arbitrary vector spaces like polynomials by rewriting them as their coordinate vectors and then doing the relevant computation with the coordinate vectors.